Next, we want to look at the importance of transfer learning. As a reminder, we start with some pre-trained network. Again, let's assume there's some input image and we have some image classifier. So there are going to be several layers, layer 1, layer 2, and then there will be the last layer. And the last layer computes some output depending on the number of classes. Typically, we'll do ImageNet pre-training, so this will be a classifier that computes 1000 outputs. And then what we're going to do is we're going to take out this last layer and we'll insert a new layer, L new, that has a different number of classes based on our new dataset that we're interested in. We're going to look at results from this particular paper that did a lot of experiments with regards to transfer learning. And this paper compares the performance of 16 different classification networks on 12 different image classification datasets. There are multiple different versions, in particular 3 versions of transfer learning that the paper looks at. First is logistic regression. We initialize with pre-trained ImageNet weights, and we cut off the last classification layer as shown. We add a new classification layer with random weights, and we only train the last layer weights and keep all earlier weights fixed. That means only the last new layer will be trained. The weights of all previous layers will be frozen during training. This is, again, what we call logistic regression. So it's logistic regression using pre-trained features. Then we have fine-tuned that follows pretty much the same outline. We initialize with pre-trained ImageNet weights, we cut off the last classification layer, we add a new classification layer with random weights, but we are going to train all layers. No weights are going to be fixed. So this is the most popular way, and this is called fine-tuned here. As we will see, as expected, fine-tuned pretty much gives the best results. And then we have the idea of just random initialization. In some sense, there's no transfer of weights, there's only a transfer of the architecture. So we are going to take an architecture that did a great job on ImageNet, and then we transfer it to a different classification task. So the steps are, we're going to cut off the last classification layer, we add a new classification layer, initialize all weights randomly, and then we train all layers. So no weights are being copied over from ImageNet to training on the new dataset. All right, first, pre-training is important. Let's try to look at this figure that shows a very large number of experiments at once. What we have is we have multiple architectures, for example, Inception V1 or ResNet 50 V1 or NASNet A large that are being trained in each experiment. Then we have different datasets, so for example, Food 101, Sci-Fi 10, Cars, or Flowers. For each of the datasets, we are going to look at these 3 versions of transfer learning: logistic regression, where just the last layer is being trained; fine-tuned, where weights are copied but all of the layers are being trained; and then random initialization, where the architecture is being copied but no weights are being copied and all the layers are being trained. So let's look, for example, at Sci-Fi 10. What we see here is that the orange bar is the highest, giving us the best accuracy, and therefore this tells us that fine-tuned is the best version of transfer learning on this particular data set. And then next we have random initialization, and last is logistic regression. Of course, this is the result after a reasonably long training time. So let's see if we can see this picture also repeated in other data sets. So we see the same in cars. Fine-tuned is better than random initialization, which is better than logistic regression. So this is the general picture. Fine-tuned is better than random initialization, which is better than logistic regression. There are some exceptions, maybe VOC 2007, random initialization is worst, DDT is also different, PETS is also different. So we'll discuss why that is shortly and what the difference between these data sets is. Now, time-wise, logistic regression takes much less computation time, that means much less time to fine-tune, than fine-tuning all the layers, and then random initialization takes even more time. Something to remember is that for each of the bars, let's look again at CIFAR 10, what we see here are results for all the different networks. So it's not that clear to see because there are like so many different, 16 different networks that all have a different icon here. And one would need to look at the paper or really zoom in to see what the best networks are. But for some of the examples, let's see here, for example, for cars, maybe this triangle here is Inception V4, and here the top performers, Inception V4. So there is a pattern that these inverse triangle-shaped ones, Inception V4, they tend to be the best in many of the tasks. This figure here compares training from random initialization with fine-tuned training. And one point on this 2D plane corresponds to one architecture trained on one dataset, where the dataset gives the color coding and the shape of the point tells you which architecture was used. And since almost all the points are above this diagonal, this tells us that fine-tuning almost always is better than training from random initialization. So the impact of regularization is a bit less clear, and I don't want to oversimplify it. There are several details in the paper. So regularization can be beneficial or harmful. So what we see here is one experiment where different types of regularization were being tried. And what do they mean? Batch norm scale is there's some bias term for batch norm. Label smoothing means label smoothing is being used or not. Dropout means dropout is being used or not. And auxiliary head means there's an auxiliary classification head used during training. And one thing that is also not really shown here is what is the regularization during pre-training and what is the regularization used during training. And so one thing that the paper says is that they recommend to really, if you pre-train with one set of regularizers, then also the fine-tuning should use the same set of regularizers. But for example, what we can see here, when we go from maybe this second column to the third column, that actually label smoothing, when it is disabled, that is actually better for transfer learning. So label smoothing might help the training on ImageNet, but it might not help, or it actually hurts transfer learning. But also, if you look at the y-axis here, one has to note that these differences are fairly minor. Also here, dropout may or may not help that much. So for the red curve, actually dropout makes almost no difference. Here are several conclusions. So ImageNet accuracy predicts performance of logistic regression on fixed features, but regularization settings matter. So in general, having a better ImageNet classification architecture will give you better results if you do this simple logistic regression transfer learning. ImageNet accuracy predicts fine-tuning performance. So this is one general advice derived from this. Just pick the best possible network on ImageNet to use as building block for your other tasks. Third, ImageNet accuracy predicts performance of networks trained from random initialization. So not only the data is valuable in transfer learning, also what you learn about architectures, just using the latest architectures, is also good if you cannot pre-train them. ImageNet pre-training does not necessarily improve accuracy on fine-grained tasks. There are some details about different types of classifications. So fine-grained tasks are one where you have to find kind of very subtle details between different classes. So an example might be if you just want to distinguish bushes, trees, and flowers, but then if you want to distinguish subtle differences within certain types of flowers, then this would be more like a fine-grained task. Next, ImageNet pre-training accelerates convergence. So a big reason why pre-training makes sense is simply because you can train much faster. And then last, accuracy benefits of ImageNet pre-training fade quickly with dataset size. So if you have a very small dataset, then it is really important to have the weights from ImageNet. If you have a really big dataset, maybe that's even bigger or as big as ImageNet, then ImageNet pre-training might not help you all that much because your dataset is so large that it can simply compute its own features well enough. Again, there are these accuracy benefits getting better final performance, and there are benefits about training faster. So this should mainly talk about getting higher accuracy. So just if you want to train really quickly, then having some weights to initialize is very important. So this is another very interesting paper that does large-scale experiments, rethinking ImageNet pre-training. So this paints a slightly different picture, and this paper says that ImageNet pre-training might only provide accelerated training, but no accuracy improvement for object detection at least. So these authors, they were into object detection, and they noted that if you train long enough, at least for object detection, that pre-training doesn't really help to give you a better metric, a better performance metric. So it only helps you training faster if you have limited time. So this paper, they really trained for quite a long time, probably more than most of you would be willing to do to get these type of results. So here's a schedule where you train for some time, and this general picture is that if you do random initialization as shown in purple, you train and you improve, and then maybe this is like a jump that you get through adapting the learning rate. So you would go up, and then you would end up here somewhere. So this is the idea of training with random initialization. But if you use pre-trained weights, then you would go up here, then maybe again change the learning rate, and you would end up here. And so this was basically the conventional wisdom that pre-training helps you to get the best final performance. However, what the authors argue here is that if you actually train for longer, then the gap between random initialization and pre-training will pretty much be closed. So, for example, if you train very long time and then only at the end fiddle with the learning rate, we see that the difference between pre-training and random initialization is pretty much gone. So here we see different tests, and then there's bounding box average precision and mask average precision. Let's just look at the first two. These first two compare random initialization and training with pre-training. And so what we see is across all these 4 different tests, comparing these two, these two, these two, and these two, that actually the random initialization gives slightly better results. And then comparing these other two, this is mask average position, again we see a very similar picture that is like slightly better using random initialization rather than using the pre-training. So